Solutions. Solutions are homogeneous mixtures, which means they are uniform. They have one phase when you look at them. The components of a solution are solute, which is dissolved, and the solvent, which does the dissolving. Normally the solvent is water. The ease with which a solute dissolves depends on two things: the change in energy content and the change in disorder. And we've looked at entropy back with thermodynamics. The change in energy content is called the heat of solution and depends on three types of interactions. Consider the solution formed by dissolving KCl in water. When you dissolve KCl in water, there are two types of energies involved: the crystal lattice energy, which deals with solute-solute interactions, and the hydration energy, which deals with these two types of interactions. Now, the crystal lattice energy is defined as the energy released in the formation of 1 mole of the solid. For our purposes, we want to dissolve KCl, so we're going to flip this equation around. We're going to take the solid and break it apart first into ions. And so this process, or the dissolving process, is going to be endothermic. Once we have ions, we're going to hydrate those ions, surround those ions with water. This is called the molar hydration energy. It's defined as the amount of energy released in the hydration of 1 mole of ions. So here's a picture of what happens in the hydration process. The ions that are now separated from the solid are surrounded or solvated by water molecules. So for the dissolving of KCl, two things have to happen. First of all, we take the solid and we break the solid apart into ions. That's the crystal lattice energy. Then we're going to take those ions and surround those ions with water molecules. That is the hydration energy. If we add up the hydration plus the crystal lattice, we get the heat of solution, which for KCl is positive 12 kilojoules. Because we are increasing entropy, increasing the disorder, this favors the dissolving process for KCl. Ionic and polar solutes tend to dissolve in polar solvents. How do you know if something is polar? If the central element has lone pairs. So we go back to the Lewis structure. If the central element has lone pairs, more than likely it's polar. For example, KCl dissolving in water. Why does KCl dissolve in water? Because KCl is ionic, which means it breaks apart into ions when I put it in water. And water, when I draw the Lewis structure, has lone pairs around the central element, oxygen. So water is polar. So ionic, KCl, will dissolve in polar solvents. Likewise, nonpolar solutes tend to dissolve in nonpolar solvents. For example, iodine. Iodine looks like this. The reason this molecule is nonpolar is because there's no electronegativity difference between the atoms. They have the same value for electronegativity. So this molecule is nonpolar. Carbon tetrachloride, without drawing all the electrons around the chlorines, looks like this. No lone pairs around the carbon. So this is nonpolar. So iodine, nonpolar, will dissolve in carbon tetrachloride, nonpolar. So we say like dissolves like. Polar will not dissolve in nonpolar and vice versa. Electrolytes. When ionic compounds dissolve in water, the ions separate from the crystal and migrate through the solution. They can conduct an electric current. These are called electrolytes if they can conduct an electric current. There are strong, weak, and non-electrolytes. Strong electrolytes tend to be ionic compounds. When I put an ionic compound into water, it completely separates into positive and negative ions, which can conduct an electric current. Weak electrolytes, we're not going to worry about too much right now. This gets into more weak acid, weak base chemistry, so we'll talk about this later. Non-electrolytes tend to be your covalent substances, your non-metal compounds like sugar. When you put sugar in water, it does not break apart into ions, and so it will not conduct an electric current. So non-electrolytes, non-metal compounds. Ways we can tell concentration of solution. We can do percent by mass, mass of solute over mass of solution. We can do molality, which is moles of solute divided by kilogram of solvent. Let's look at a molality problem. We want to find the molality of KCl dissolved in water. So we're going to take the moles of KCl, that is my solute, divided by kilograms of water, which is my solvent. So we have 45 grams of KCl. Convert that into moles, so the molar mass. Divide that by the kilograms of water, which would be 1.1 kilograms. So the concentration, 0.548 molal. Just use a small m for molality. We can also use molarity to determine concentration. Molarity is moles of solute over liters of solution. In this problem here, we want to determine the molarity and the molality. So we have my solutes, lead nitrate, and we're dissolving that in 500 mils of solution. Part A, what is the molarity? Molarity is moles, solutes, which is lead nitrate, divided by liter of solution. So we have 150.1 grams. We need that in moles, so we need the molar mass. Divide by liters of solution, which would be 0.5 liters. So the concentration in molarity is 0.907 molar, capital M. Part B, what is the molality? Molality uses the same numerator, it's the denominator that is different. I do know that I have 500 mils of solution, and I know the density of the solution is 1.252 grams per mil. So I know the solution has a mass of 626 grams. That's for the whole solution. If I want just the mass of the solvent, which is water, I could subtract the grams of lead nitrate. So the mass of water, which is my solvent, is 476 grams. Molality then, we're going to take the moles of the lead nitrate. We had 150.1 grams, divide by the molar mass. Divided by kilograms of solvent. We have 476 grams, so 0.476 kilograms. So the concentration in terms of molality is 0.953 molal, the small m.